Boy, that was a terrific knuckleball. That one got up to home plate and just kind of wiggled. Almost waved by to Blake Swihart.
What just happened there?
The knuckleball has been baseball's most puzzling pitch for over a century. The pitch darts and changes direction as it floats to the plate with almost no rotation at all, making it hard to catch, even harder to hit, and puts less strain on the pitcher than a fastball or breaking ball. Pitchers who have mastered the knuckleball have won Cy Young Awards, made the Baseball Hall of Fame, and pitched well into their late 40s, all while confusing hitters and scientists alike with the pitch. So what makes the knuckleball dance? In this video, I'll be breaking down the fluid mechanics of the knuckleball, what makes it different from a fastball, and what makes the pitch so unpredictable. Unlike most other pitches, pitchers grip the knuckleball with their fingertips or fingernails. While the fastball is thrown at an average spin rate of 2,300 RPMs to maximize lift, the knuckleball is thrown at just 150 RPMs, sometimes less than a single rotation on its way from the pitcher to home plate. And while pitchers throw their fastballs harder and harder every year in the major leagues at an average of over 90 miles per hour, the knuckleball effect has been observed in pitches between 63 and 81 miles per hour, or 28 to 36 meters per second. This range is very close to the drag crisis range given by the Reynolds number for an air fluid flow around a baseball, which I will discuss later. Before we look at Reynolds numbers, it's important to understand how lift affects different pitches. Let's first look at the equation for the conservation of linear momentum. Despite the effects of gravity, body forces are typically small enough that researchers of ball sports tend to neglect them. Surface forces, however, depend largely on the Magnus effect and drag forces of the ball. For a fastball, the Magnus effect comes from the backspin of the ball, where faster moving air above the ball and slower moving air under the ball create a pressure gradient due to Bernoulli's principle, and thus an upward lift force on the ball as it flies to home plate that can alter the trajectory of the fastball several inches. On the other hand, the knuckleball does not spin, so it does not experience the Magnus effect, so its lift forces are mostly, if not entirely, dependent on the orientation of the seams of the ball and how they disrupt the fluid flow. Shown here is a graph of the lift coefficient as a function of the ball's orientation. As you can see, it's very similar to a sine wave. The slowly rotating seams on the ball are one of the keys to the pitch's odd movement, as a small change in orientation of the ball can disrupt airflow, change boundary conditions, and alter this lift force. This is why knuckleballs actually need to have some non-zero spin such that the magnitude of the forces can change as the orientation of the pitch changes on its way to home plate. One of the keys to the strange movement of the knuckleball is a phenomenon called the drag crisis, which occurs when the Reynolds number, the ratio of inertial to viscous effects in a fluid flow, increases well above its transition to a turbulent flow. In this Reynolds number range, the pitch undergoes a drag crisis, where the drag coefficient of the ball drastically and suddenly drops. Thus, the ball is much more affected by its orientation and surface conditions, and any sudden changes in drag forces can cause the ball to change direction unpredictably. For a smooth sphere through air, this range occurs at a Reynolds number of around 300,000. However, a baseball isn't perfectly smooth, so it has a drag crisis range between 100,000 and 200,000. As I mentioned before, the Reynolds number, shown here, describes the ratio of inertial effects to viscous effects in the fluid flow. It's equal to the product of air density, relative fluid velocity, or velocity of the baseball, and ball diameter over the viscosity of the flow. Rearranging our equation and plugging in our known values, we can solve for the velocity of the baseball at the upper and lower ends of the drag crisis range. This is equal to a velocity range of 19.3 meters per second to 38.75 meters per second, or 43 to 84 miles per hour. It makes sense then that three of the most accomplished knuckleball pitchers in the MLB threw their knuckleballs between 65 and 75 miles per hour, smack in the middle of this drag crisis range, to stay in the crisis zone for as long as possible as the ball slows down on its way to the plate. This is also why a knuckleball at 90 miles per hour simply wouldn't work. It wouldn't have the same knuckle effect as a slower pitch. Lastly, we can elaborate further on the lift coefficient of a knuckleball, modeling it as a function of its orientation. Here, researchers computed a superposition of the forces produced by the vortex shedding at each individual stitch of the ball, where P is the stagnation point, SI is the location of the pitch, SI star and P star are the Z components of these respective variables, and A0 and A1 are the weight coefficients. But that's a discussion for a more advanced course and another day.